5 people that can hear me. So what I want to do is pick up where we left off last time. I introduced this idea of resistivity, and I want to dig a little bit deeper into this. So we started with the idea of a simple model. We can generalize this, but our simple model is our conductor is this, say, piece of wire, and it's made of something. It has a length L and a cross-sectional area A. And I gave you this formula to calculate the resistance of this wire based on the length, the cross-sectional area, and a property of the material that the wire is made of, which is going to be called the resistivity. The resistivity is a different thing than the resistance. It's signified with this small Greek rho, and it has weird units, ohm meters, whereas the resistance has units of ohms. So the resistivity is going to be a typical number for, a specific number for different materials. So copper will have a different resistivity than tungsten, than seawater, than mussel. What we saw was some materials have really low resistivity, this property of the material that allows for the free flow of charge through that material, so that this number is small. If I put it over here, then the resistance of the wire is going to be small. But the actual resistance is going to depend on the physical dimensions of that material once you've started to form it. So if I have a longer piece of copper, than a shorter piece of copper, both of those pieces of copper are going to have the same resistivity, but they'll have different resistance because one of them is longer than the other. And by the same token, if I goof around with the cross-sectional area of that wire, I'm going to get a different resistance number, even though it's made of the same copper and it would have the same resistivity. Okay, easy to get these two confused. They have similar symbols, they have similar names, they have similar units. So it's worth to kind of take a pause and convince yourself that you know the difference between these two, so that it doesn't trip you up at some point. So we saw that there's materials with low resistivity, which we call conductors. They have not much resistance to the passage of charge. We have things that will allow charges to pass, but kind of grudgingly, and we call these poor conductors, things like seawater, mussel, fat, things like that. And then we have things that are just downright bad conductors, and because these resistivity values are so large, we call them insulators. They really resist the passage of charge, and that can be a useful thing if you want, to electrically insulate something. If you don't want current flowing through it, if you want to protect a human from getting shocked, these type of materials are quite useful for that. So the part that I did not get into was trying to use this in an example. So if you go to the store and you buy an old style light bulb, not an LED or some kind of other type of light emitting device, just an old Edison type light bulb, you look inside, there's this coil of something. It's tungsten wire. Usually it's tungsten wire. And we have a current flowing through that tungsten wire. It heats up the tungsten wire because you have these billions and billions of charges going through it. And that heating of the wire, then the wire glows. It just emits light. So typical values for a light bulb, if I go into the store, then I'm going to have a resistance something like 240 of these ohm units. Resistivity for tungsten when it's hot is this value. You can look it up in the table in your book, or you can look it up online. It's about 5 × 10⁻⁷ ohm meters. Don't forget those meters in the ohm meters for resistivity. And then the cross-sectional area, if I look at this wire head on, in the statement of the problem, I'm telling you that the diameter of this wire is 0.4 millimeters. and I have to divide that by 2 to get the radius. I square that, multiply by pi, I can get that cross-sectional area. So I get this absurdly small number for the area, 1.26 times 10 to the minus 9 meters squared. Now, my governing equation for this problem I know is relating resistance and resistivity, length, and cross-sectional area. I've got to peel out this length, because what I'm trying to find is, what is the length of filament inside this light bulb? I have this light bulb, I don't know, it's a coil of wire. If I stretched it out, how actually long would this be? I have all these other inputs, and that's the only thing I don't know. I know the cross-sectional area, I know the resistivity, I know the resistance. So the only unknown is L, so I can solve for that. Just, you know, peel out the L from this, put everything else on the other side of the equation. And now finally I can put in some numbers. The resistance, the big R, is 240 ohms. The cross-sectional area is 1.26 times 10 to the minus 9 meters squared. And the resistivity is 5 times 10 to the negative 7 ohm meters, which I looked up on Wikipedia, or I looked up in our textbook in the table of resistivities for different materials. All that being said, I can now use my calculator and just punch in these numbers, and I get 0.6 meters. You could look at this 2 different ways. I could do it the quick and easy way, which is, hey, I put everything in SI when I started up here, so I'm going to get the SI unit of length when I'm done, which is meters. Or you can do you can do your due diligence, which never hurts, and carefully check the units work out. So I have ohms here are going to cancel out. I have meters here, I have meters squared there. So one of those meters is going to cancel out, and I'm left over with meters. So the somewhat surprising result of this is, if you crack open a light bulb and with typical values, you're going to get something like 60 centimeters of this tungsten wire in there, this very fine wire. It's very hard if you've ever tried to do this, but it's about 2 feet of wire within this light bulb. Okay, so that's our numerical example on resistivity. If you actually were ahead of me in the notes and you saw a previous version of this problem, I again had a little typographical error in my notes where I was saying the radius was 0.4 millimeters, and if you tried to calculate that area yourself, you would have gotten the wrong number. The 0.4 millimeters is the diameter, so just be aware of that if you had gotten ahead of me and were looking at these notes before today. Okay, so I'm going to close that out. This is your opportunity to stop me, ask me any questions, or in the chat or audio. Feel free to do so. What I'm going to do is move on a little bit here. I remind you that in your participants window, at the bottom, there's this little bunch of knobs that you can tweak and push that say, one of them is go slower. And I invite you to use that. If I'm going too fast, please don't hesitate. I always have one eyeball kind of looking at that to see if I'm going too fast. So use that as your brake pedal if my lecture starts spinning away. Now, what I want to warn you is, in your textbook, in electrical engineering books, in physics books, in all kinds of books, you'll see different symbols for this idea of a potential difference. I have, up until now, used a single symbol, which is this clumsily drawn battery with a negative and a positive, showing the higher potential is on this side, the lower potential is on this side. You will notice in your textbook that I think they use this symbol, which is this kind of hieroglyph of long, short, indicating a battery also, but a little bit easier to draw than this cartoon. And this is kind of a standard symbol. What this indicates is the higher potential is on this side, the longer side, the lower potential is on this side. And I also said that sometimes in the battery, we refer to that in this old-timey jargon, which is electromotive force. It just signifies a potential difference. I don't want to confuse you, but it's out there, so I don't want you to think that my notes are the only way of doing this. I've also seen it sometimes, and sometimes I'll be, shorthand notation where you have one long, one short is kind of a short version of that. And again, this just means the same thing. These all just represent a source of potential difference in your circuit. So, you know, it's like going to a different part of the country and people say things slightly different, although they mean the exact same thing. It's that kind of idea here. Okay, so what we talked about last time was Kirchoff's junction rule. Kirchoff's junction rule is this idea that if I have a mess of wires joining at a point in space, then the current going into that mess of wires has to be equal to the current going out. So in this simple case, we have 6 amps, 3 amps, 1 amps all going into this junction. I better get 10 amps coming out of that junction, or else I've lost some charge somewhere. It's escaped and there's nowhere for it to go. So that would violate conservation of charge. So our statement of conservation of charge in the context of circuits is, you know, the sum of the currents into that junction is equal to the sum of the currents out, okay? The new law that we want to introduce today is this idea of the loop law. And this is that the change in potential around any loop is 0. This one looks a little bit, I don't know, you know, we can make any simple idea look scary by putting it in Greek symbols. So we have this summation symbol, we have the delta symbol, we have V and it equals 0. Basically what this is saying is if we go around a circle, my finger is disappearing. If we go around a loop anywhere in a circuit and get back to the place that we started, then the changes in potential as we do that, the increases and the decreases have to all cancel out. And you know, any increase in potential that we have is going to be matched by an equal and opposite decrease in potential. So this looks a little bit weird. It looks a little bit scary at first. I hope that, you know, I'll do a couple examples of this and we'll see what, you know, we'll see that it's not really anything that you should be intimidated by, I hope. So what I'm going to do is very briefly mention the loop law rules of how to apply this, and they'll seem a little bit out of context until we actually see them in effect. So I'm not going to spend too much time on this other than to get them all in one place. So the first thing what we have to do is we have to assume a direction of current flow around our loop. You know, we can go clockwise or we can go counterclockwise. We're never going to know, or usually we will not know at first if we've made the right guess. But that's okay, because what will happen is if in the end you solve for the current in this loop and you get a negative result, you just, you know, you go back and you say, hey, I chose the wrong direction and it's actually the other direction. That's what happens when you get a negative current, is it's just, you know, you made the wrong guess in the first place. You got a 50% chance. It's no big deal if you get it wrong, because you just know you'll get the negative in the end. Okay, and again, I'll hopefully clarify that with an example in a moment. As you travel around the loop, if you go upwards in potential from a low potential to a high potential through a battery, then your change in potential is greater than 0. It's a positive number. If you force the current to go the wrong way through your battery for some reason, then you're going to have a negative. We're going from this higher potential to lower, then that change in potential is going to be negative in our equation. Okay, again, I'll show an example of this in a moment. And always, as the current drops, as the current flows through a resistor, the voltage difference across that resistor from the direction that the current is coming to the direction that it is going, that voltage drop is going to be negative. All of these, I appreciate, they probably seem out of context at the moment, and I'll try to put them in context right now. So let's take a look. We have an example here. If you will, stay with me on the left-hand side of the picture for a moment. I don't want to overwhelm you with too much. So if you look at this, this looks messy all of a sudden, but it's really not so bad. We have a battery. It's a 10-volt battery. We have 2 resistors, a 5-ohm resistor and a 5-ohm resistor. And then it's connected with wires, and I've put a lot of markup on this that makes it look a lot more busy than it actually is. It's just a simple circuit with 2 resistors in it. It's one step beyond what we've seen before with a light bulb. Now I have 2 light bulbs in here. So I can, and then each of these points in the circuit, I am labeling with a letter A, B, C, D, E, and F. Okay, so I'm just labeling locations in our circuit. This will become, much more complicated with many more resistors, or we could throw other circuit elements in here. But for now, we have a kind of a simple circuit, and I'm labeling 1, 2, 3, 4, 5, 6 different places. So what's happening in this? I'm going to apply Kirchoff's loop rule to this. Let me try to make this a little bit smaller so everything fits on one page. So in this, we have a change in potential as we move along this circuit. I've assumed that the current is going this way. I'm telling you that 1 amp in this example, I'm giving that the current is 1 amp flowing in this direction. I'm giving that the first resistor is 5 ohms, the second resistor is 5 ohms. So what are the changes in potential as I move around this circuit loop? Well, going from A to B, from the negative terminal, the low potential terminal, to the high potential terminal of the battery, we have a 10 volt increase in potential going from here to there. So in my diagram, finally, we'll take a look at this diagram on the right. What I'm showing here is potential, which is measured in voltage, as a function of the position in the circuit. So those 1, 2, 3, those 6 different places, A, B, C, D, E, F, are shown on this axis, and the value of potential is shown on that axis. Going from A to B, I have an increase of 0 to 10 volts. So that's signified by this increase from 0 to 10 volts there. As I go from B to C, this is a bit subtle, but in these diagrams, you are to assume that these kind of connecting wires have no resistance at all. Okay, 0 resistance. All the resistance is going to be actually specified by, these symbols that show resistance. And in reality, is this realistic? Can we make a wire that has no resistance? No, not at room temperature. We cannot. There are superconducting wires. That's not what we're talking about here. This is an idealization. It's a approximation that whatever these connecting wires are, they're much, much smaller than the actual resistances that we place in our circuit. Okay? So again, as often is the case in physics, we make this approximation, but if this resistance of this connecting wire is 10 to the minus 9 ohms compared to 5 ohms, who cares? It's good enough. And if we really needed that precision, we could make a correction for it. But in these diagrams, what you are to assume is that there's no resistance in these connecting wires. If there's any resistance in your circuit, it is given at the points where these jaggedy, monster teeth resistances are shown. Okay, so from going from B to C, I have no resistance. So there's going to be no potential change going from B to C. And that is signified in this plot. Going from this point to this point, I stay at 10 volts. The consequence of that is anywhere along this, from this positive terminal over to the start of the resistor, is at the same potential 10 volts. Okay, then what we have a current. This current is the same all the way through the circuit, because we know that the current is from the first junction rule. There's no junctions. There's no places where this could split off and go anywhere else. So if I put 1 amp in here, it's going to be 1 amp all the way around. I know that there's 1 amp flowing through this resistor. If I have 1 amp through 5 ohms, I'm going to have a voltage drop, which is given by Ohm's law. Delta V equals IR, I times R. So 1 amp times 5 ohms, and that's going to give me 5 volts. Back up here, the current is flowing through a resistor. This is going to be a negative potential drop. So I know that I have minus 5 volts going from point C to point D as I move across this resistor. I have a 5 volt potential drop as I move from this point to that point. Again, perfect wires going from D to E. So D to E, no change in potential, flat line here. It stays at 5 volts. And then I have one more potential drop as that current flows through this 5 ohm resistor. I'm going to have another 5 volt potential drop as I go through this 5 ohm resistor. And that is signified E to F. So I get E to F, and I get back down to 0 volts. Again, showing this all in the numbers. A to B, we increase 10 volts. B to C, nothing happens. C to D, we lose 5 volts as we go through this resistor. D, I will answer the question just in a moment. D to E, we have no change. E to F, we have minus 5 volts. And then F going back to A, because it's this perfect wire, we have no change. So all together, we have plus 10, minus 5, minus 5, plus 10 minus 10 is equal to 0. This is Kirchoff's loop rule. So the sum of the voltage changes around this loop is going to be equal to 0. Now let me read what the question here is. How do you determine if delta V is plus or minus if it flows through a resistive going right left? So if somehow the so this is a question, how do you determine if delta V is positive or negative? Anytime that you follow the flow of current, whether it's going left or right, up or down, whatever, that's going to be regarded as a negative as a negative potential, as a potential drop. The potential will always drop as the current flows through a resistor. So if I had the current going the other way, this would be a little bit counterintuitive, but yes, it would be negative going this way. It would be negative as it went from D to C. It would be negative as it went from F to E if we had the current going the opposite way. Okay, so I hope that answers your question. Basically, you know, you've got two situations. One is you know the flow of current going in. Here we knew the flow of current because it's going to go from positive to negative. And if we're following the flow of current, that potential, you'll hear people say about a potential drop across a resistor. That's what we're talking about. The potential drop is it's a negative value. It's going to get less as you go across the resistor. If I had turned that battery around and the current was flowing this way, then the potential drop would be in this direction. You'd be higher potential, lower potential, higher potential, lower potential, always going to lower potential as you go in that direction of flow. So there's, as I was saying, there's two ways that you might approach this. One is when you know the current, right? And in this case, I gave you the current. The other is the kind of the more ambiguous situation where you had to guess the current. You had to guess if I hadn't told you, if I had put a little block over this battery and you didn't know which one was the positive terminal and which was the negative terminal. I put a little cloth over that part of the circuit and you didn't know. And you had to make this guess about the direction of the current. It's okay as long as you stick with your convention. Everything will work out fine, even in this loop rule, because in the end, the negative will just you're going to sum to 0, but you'll sum through a negative number as opposed to summing through positive numbers. It will work out for you. Okay, so I hope Francis that answers your question, and if not, I'm happy to take another swing at it. But that's our loop rule right there. And again, the subtle part here, if I give you the value of the current, you don't have to make any guess about it. If I don't give you the value of the current, you have to make a guess. But in the end, you would wind up with a negative current, and that's okay. It just tells you that your guess was wrong in the beginning. So let's take another look. Francis, if I didn't get a response on whether that was clear or not, so let's take another look at a slightly more complicated example. And feel free to just bang away at your question if it's not coming through. Hopefully, this one gives you a little bit more of a direct example of maybe what you're asking. So I have a more complicated example here, which is. Oh, okay. So thank you very much. So that sounds good. So we have a more complicated example here. I've taken two batteries. Remember, this is the symbol for a battery now, and I have the positive terminals wired together. Why would I do this? I don't know. I just want to burn out a battery, or I want to charge a battery, or I want to do something weird, or maybe I don't know what I'm doing and I'm just randomly hooking things together. But I have the positive terminal and a positive terminal of a battery. This is a 9-volt battery. This is a 6-volt battery. In between them, I've connected a 40 ohm resistor and a 20 ohm resistor. The 20 ohm resistor is between the negative terminals. The 40 ohm resistor is between the positive terminals. And what is going to happen here? So what is I? This is the question that, I'm given these values. I've given these two potential changes. I'm given this 40 ohm and 20 ohm resistance. What is the current? Now, I went in here and I made a guess that the current would go in this direction. I think this is an intuitive guess because, hey, this voltage is higher than that voltage. So even though this guy probably, if it was left to its own devices, if there was no battery over here, there would be a current flowing in this direction, right? That's our normal circuit. But because this potential is greater than that potential, kind of intuitively, I'm going to guess probably the current's flowing this way because this 9-volt battery is stronger than a 6-volt battery. And I'm making that guess, but in the end, if I made the wrong guess, I'm just going to get a current that's negative, and that's okay. Because it just tells me the direction that I initially guessed was incorrect. So there are 4 places where the potential change here. This is a direct application of the loop law. So what I'm going to do here is I increase by 9 volts here. I have a drop of resistance along the current flow across this 40 ohm resistor. I have a change of 6 volts of this battery, and then I have another potential drop as I go through this 20 ohm resistor. So how do I deal with this mathematically? This is my loop law here, and all I want to do now is start plugging these in with care as to whether they're positive or negative. So this one, I'm going in the direction of current flow. If you go back 2 pages in my notes, it has the rule for this, and that's the normal direction of current flow. So I'm going to call that a plus 9 volts. I have a current flowing through a resistor, and because I'm going along the direction of the current flow, I consider that a drop in potential, a negative change in potential. So I'm going to signify that as delta V 40 ohms, right? The 40 ohms is just a subscript to signify I'm dealing with this resistor. And then I'm going the wrong way through this battery. I'm driving the wrong way down this battery street. I don't know. And it's going in the positive terminal and out the negative terminal. And because of that, we want to make this a negative 6 volts. We don't count that as a positive 6 because this current flow is going in the wrong direction or the unusual direction. And then we have a potential drop across this resistor, and for the same reason that I said for this resistor, that's going to be negative. So I signify that with a 20 ohm subscript there. Now I can start applying Ohm's law and putting in numbers. The current is unknown, but I know that this potential drop across this guy and the potential drop across this guy is just an Ohm's law type thing, that delta V is equal to IR. Delta V equals IR, Ohm's law. So I don't know I, it's an unknown. That's the one unknown in this problem. Could you please zoom up on the PDF a little bit? Absolutely, sure. Trying to put too many things on the screen at one time. So let me see. So what we have here is the potential drop across this guy and the potential drop across this guy is just given by Ohm's law. So we have delta V, the potential across these guys, is equal to the current times the resistance. So that's what I'm doing right here, is I'm applying Ohm's law to get a little bit more information about this delta V across the 40 ohm resistor and this delta V across the 20 ohm resistor. It's just the current times the resistance, the current times the resistance. Okay, much better. There we go. Okay, sorry about that. So now it's just a mathematical problem. Now we're doing algebra. So we have 9 volts 6 volts. I'm bringing those together. We have current in this unknown current in 2 different places in my problem. So I have I times 40 plus 20. I just took out the common I, the common negative I actually. And now I'm left over with 9 minus 6 is equal to plus 3. And 40 plus 20 is equal to 60. So I have plus 3 volts minus I times 60 ohms equals 0. Now I can just, put this guy on the left-hand side of the equation, put this guy on the right-hand side of the equation, and I can solve for that unknown, which if it's easy to lose track of what we're trying to do. The initial question was, what is I? What is I? It sounds weird coming out of my mouth. What is I? So I equals plus 3 volts over 60 ohms. I punch that into my calculator and I get 0.05 volts per ohm. And SI units for voltage, or SI units for potential, SI units for resistance. So I'm going to get SI units for current, which is amps. So the number comes from this. The units comes from the fact that I know that a volt per ohm is equal to an amp, or that I did everything in SI, so I better get the SI unit of current in the end. So in the end, I get 0.05 amps for the current that is flowing around this slightly more complicated circuit. Okay? Now, I'm going to hit you over the head with a bunch of examples today. Let's do one more example. And this was sent to me by Dawn, so sorry for the change in handwriting. She would like you to see this for so that you're prepared for your labs. And what we got here is a slightly more complicated circuit. So I have a 9-volt battery in the middle of this circuit. I have a resistor of 30 ohms over here. I have a resistor of 40 ohms over here. Let me make this bigger. And what we're going to try to do is analyze this circuit and figure out what the currents are. So my process in this is, first we find all the junctions. Where are the junctions? The junctions are wherever the wires, where we have more than 2 wires coming together. This part right here, this little kink, is not really, it is a junction, but it's like 1 wire coming in, 1 wire coming out. We don't really have to analyze that because nothing tricky is going to happen. Here is a junction in the sense that I have a current I1 flowing in this direction, and that I1 now splits. So this is our first junction. That current splits into I3 on this wing and I2 on this wing, and then joins back up again on this junction right here. So our two actual junctions are here and there. I've identified those junctions. And now I label the current between the junctions. I'm going to call this one I1, and then for lack of a better idea, I'm going to call this I2, and I'm going to call this I3. All right, so that's our start. Now we apply the junction rule, our first Kirchoff law, which is that I1 is going to be the sum of I2 and I3, because the charge can't get out of this circuit. It can only, it can split into this branch and this branch, but when it joins back up again, you better not have gained any current, you better not have lost any current in that process. So we got I1 is equal to I2 plus I3. Okay, you guys with me so far? I hope. If not, just throw me a question in the chat. Now the next thing that we got a yeah. Fine. So let's try to break down what we can do next. We can now find I2 using the loop law. This is a little bit subtle, but what we have here is we have a loop here and we have a loop here. So we could apply that loop law on both of those loops. I only showed you examples so far with a single loop, but now we have a circuit with 2 loops. You can apply this on any loop that you find in a circuit. So my loop law is that the sum of the potential changes around the loop are going to be equal to 0. Let's focus on this loop right here. If I can draw, I don't know, can I draw with this? Let's focus on this loop right here. We're going around this loop. right? And when we go around this loop, I have a 9-volt potential increase going from low potential to high potential. And I have current flowing in this direction, so I have a voltage drop as I go through this resistor here. That's an Ohm's Law ohmic drop. So I have I2, which is the current in this loop, and this resistance is 40 ohms. So we got 9 volts minus I2 equals I2 times 40 ohms equals 0. The sum of the voltage changes around that loop is equal to 0. So that's okay. Now I can just solve for the unknown. I2 is going to be equal to 9 volts divided by 40 ohms, and my calculator tells me that's 0.225 amps. Okay, so what we did here was we found the current through this loop. Now what the heck is happening over here? We'll do the same exact thing in this loop. I have a 9-volt increase going from negative to positive, or from lower potential to higher potential. And I'm going to have a voltage drop as I go across this resistor, this 30 ohm resistor. So let's take a look at the math of this one. I can't get the picture and the math on the same page, sorry about that. But we have plus 9 volts as we go up through the battery, and then minus I3 30 ohms as we fall through that resistance. And here I can solve for I3, which is 9 volts divided by 30 is 0.3. And then I know finally that those two currents, I2 and I3, right? Again, the two loops that I'm analyzing are this loop and this loop, right? And we start with some current, which we're calling I1, and it splits into I2 plus I3. A mathematical way of saying that is, finally that I1 is equal to I2 plus I3, and the numbers we just figured out from here, 0.225 amps, 0.3 amps. So the total current being drawn out of this battery is 0.225 plus 0.3 amps is 0.525 amps. Okay, so slightly more complicated problem. And we have a question here. I thought the current would exclusively take the path of least resistance. So Francis, that in general, that's going to be a truism. These resistances are so close to each other that we're going to have some splitting of I think what you're thinking about is like extreme cases, like if a lightning bolt has the choice between going through you and through a metal bar, that metal bar has much lower resistance than you do. Here, we're actually going to get a splitting of current between them. So yes, the intuition that you're following there is correct, but usually that kind of old maid's logic, I'm not trying to call you an old maid, but that kind of common logic about what's going on is applying to, hey, if we have an insulator compared to a conductor, the current's going to go through the conductor and not through the insulator. And that's the same idea when you see a bird on a wire, that kind of thing. And I remember when I was a kid, there was always, how does the bird stay on the wire and not get shocked when there's no insulation? Well, that's true because the resistance through the wire is so much smaller than through the bird. But in this case, where we have a difference of 10 ohms between 30 and 40 ohms, you will get a splitting of the current between the two. Okay, I hope that jives with your intuition of what's going on here, and your intuition is basically correct. But usually you're not talking about stuff that has similar resistances, just slightly larger than the other. Okay, so the last thing that I want to introduce here today, and I was hoping to do a poll. We'll see how fast I can go through this without losing you guys. If I'm going too fast, it doesn't make too much sense. So let's just do it right. I want to introduce this idea of power, and power is the concept of the rate of change of energy. And when we're talking about an electrical circuit, you're talking about how much power is being used, is being consumed by the circuit. For example, a light bulb, how much energy does it take to run the light bulb? So if we have a simple circuit here and say this is a light bulb, then we have a source of potential difference, this battery. We have our resistor over here, and the potential difference typical would be something like 120 volts. the typical current would be something like 0.5 amps, and our resistance is 240 ohms. So I define the current as the rate of change of charge, or how much charge flows through the light bulb per second, the amount of charge per second. And here in my notes, I'm using a big Q and a little q. There's no significance between the two. I just noticed this afterwards. I'm not trying to signify anything different. These are both just, supposed to be the same Q. There's no meaning behind that. But as this charge flows through the circuit, it will lose energy. And if you go back to our definition of the potential energy of a charge going through a potential difference, is delta U equals delta Q delta V, right? That's just charge times potential gives me potential energy, the change in potential energy. And that loss of potential energy of your charge as it's falling through the light bulb is converted into the thermal energy of the light bulb, because the charges are picking up kinetic energy, but then they slam into the lattice of the light bulb and they heat it up and it glows. So the thermal energy of the light bulb is where where this energy is going. So this power is the rate of change, right? And if I write this, give me a second here, my notes, here's where I want to go to. If the power is the rate of change of energy per time, and my change in potential energy is delta Q delta V, then I have delta Q delta V over delta T. But just notice right here that this is the definition of current. So I have power is equal to I delta V. This is the rate at which your light bulb is going to consume energy. And if you walk into the hardware store, why can't I open my, if you walk into, there it is. If you walk into a hardware store and you buy an old-timey light bulb, this 60 watts that's on there is measuring this P equals I delta V. This I delta V is sometimes simplified. Again, it's sloppy notation, but it is what it is. It's on in many textbooks, and sometimes you'll see this, sometimes you won't. Sometimes this will be simplified with dropping the delta. And it's a little bit of a cleaner notation, but it's sloppier in the sense that we always know that what matters is a change in potential, not the absolute value of potential. It's the potential difference across the battery, that kind of thing. So sometimes that delta is dropped and we have a P equals IV. And for this light bulb, if I put in the numbers that we started with back up here, I think I gave you some numbers to start with. This delta V, this I, this R, right? Typical numbers for a light bulb. If I plug them in here, the current that's going to be drawn by that light bulb and the potential difference that's applied across the light bulb, we have half an amp times 120 volts. That gives me 60 amp volts. And I start with SI, so I'm going to end with SI. SI unit of power is watts. But if you want to see all the gory detail here, we can look at the details. An amp is a coulomb per second. A volt is a Newton meter per coulomb. And so I am going to have a cancellation of the coulombs, and I get Newton meter per second. A Newton meter is a joule, and joule per second is my unit of power, which is a watt. Last thing that I want to introduce to you guys, because it probably will be useful for your homework, is if I have this P equals IV or P equals I delta V, I can rewrite this in a couple different ways, and I'll just put this on the screen here. Because Ohm's law, delta V equals IR, I can use that to simplify this equation or change the equation. I don't know that it simplifies it, but it changes it. So if I have P equals I delta V, and then I remember that delta V is equal to IR, and I put this guy in there, then I get IR, and I can have a new expression for my power, which is P equals I squared R. The other way that I could do this is I could, instead of replacing the delta V, I could replace the I. This up here, if I solve this for I get I equals delta V over R. And if I put that in right here, then I get 2 delta V's, delta V squared over R. And, you know, a simpler way of, I need to get rid of that circle. A simpler way of writing that is V squared over R. So in all their glory, let me put them all in one place. All together, for the power that's consumed by this circuit, I could have I times V. I could have I squared times R. I could have V squared over R, where those V's are implicitly delta V's. And why would I do this? Why am I complicating your lives by giving 3 different equations? Well, sometimes you might come across a circuit where you know the current and you know the potential across the circuit, and this one's easier to use. Sometimes you might know the current and you might know the resistance, and then this one's easier to use. And sometimes you might know the potential and the resistance, and this one's easier to use. You could always, you know, you could always go back through Ohm's law and solve for the unknown quantity, but this saves you the step if you have these 3 and you realize that they're all the same equation. Okay, so do we have any questions on that? Do you want me to repeat anything or go back over anything in the notes? I'm happy to do so. We have a couple of minutes here. If not, maybe I will put up that poll that I was promising and we can close out on that. Let me see if I have, where's my, that's not what I want. Okay. Okay, maybe we'll skip the poll for today. It looks like I don't want to rush you in the last 1 minute of class and trying to solve a problem. So if there's any questions, please put them in the chat. Otherwise, have a great day, and I will see you at the next lecture. Thank you for your patience. Thank you for your attention, and have a great day. Okay.